Okay, this is the first part of our discussion on the qualitative or conceptual aspects of chemical reactions in aqueous solutions. A couple of terms to start out with. When we're talking about solutions, consist of two parts. One is the solute. The solute is the thing that is being dissolved. So like if I have a saltwater solution, the sodium chloride, would be my solute. The solvent, the other part of the solution, that is the thing that is doing the dissolving. Okay, so again, in a saltwater solution, the water would be the solvent. All right, when we're talking about dissolving ionic substances, okay, we have a situation where we get charged particles in our solution. And so we want to think about the dissolving process in terms of electrostatic forces. In other words, the oppositely charged particles within the solute and solvent are going to be attracted to each other, and the like charged particles in the solute and solvent will be repelled from one another. So here is kind of a little animation. This is our sodium chloride crystal, and these red and white molecules, that's our water. And as you can see, they are coming in, and there is an attraction between the atoms in the water molecule and our crystals, or our atoms that are in our sodium chloride crystal at the surface. And so the dissolving process is essentially these water molecules coming in and surrounding the individual ions and pulling them away from the solid crystal structure. And so looking at this, here we have our cations in this animation. That's the gray small atoms that are in our solid. And the oxygen, the big red atom here in our water molecule, that is our oxygen. The oxygen atom in a water molecule is going to be more negatively charged because the electrons in the bonds are going to be pulled more towards the oxygen atom. And we'll talk a little more later about why that is. But what that means is that when the water molecules approach our sodium chloride crystal, it's going to be the oxygen atoms that are going to rotate in and be attracted to our sodium ions. Similarly, the hydrogen atoms, the little white atoms here in our water molecule, are more positively charged, and so they are going to tend to be attracted to our negative chloride ions in our crystalline structure. So as they approach, they're going to rotate in so that the hydrogen is attracted to the chloride, and it again surrounds it and pulls it away from the sodium chloride crystal. Okay, so why does all this matter? Well, we're going to be talking about some things called electrolytes. And that terminology comes from the ability of a solution to conduct electricity. The key thing to remember here is that we normally think of electrical current or electricity as electrons moving through a wire. And that is one way that we can conduct electric current, but it's not the only way. Another way that we can have the movement of charge through a solution is with these, what we would have as our charge carriers being the positive and negative ions of the solute. And so that's kind of what we're going to be looking at, is what sorts of solutes can add ions to the solution so that the solution is then capable of conducting a current. All right, and we've got a couple of different types of solutes that we'll be dealing with. All right, one is, in this example, here's our methanol molecules that will dissolve in water. However, when they dissolve in water, they stay as neutral molecules, and so they would not be capable of carrying a charge, and so we would refer to this type of a substance as a non-electrolyte. Then on the other extreme, we have sodium chloride, which completely dissociates into sodium cations and chloride anions, and so lots of charged particles capable of carrying charge through the solution. And then kind of in the middle, we have here, this is acetic acid, and as you can see down here, acetic acid, the particles of it that dissociate, you would get the hydrogen from the acid, it's going to dissociate, and here it is shown in the way that it would actually exist, meaning it would like join a water molecule and make this H3O+, which is called a hydronium ion. We're going to be more concerned about that a little later in the year, but for now the main thing is to realize is that our acid has a hydrogen cation, and in this case an acetate anion, and they will dissociate. But however, if you look at this picture up here, you'll see that the majority of the acetic acid molecules are just staying intact as neutral molecules, and so we don't get the complete dissociation like we saw over here with the sodium chloride, and so that we would call a weak electrolyte. It would conduct a current, and as you can see up here in our picture, this solution, we have just sort of a dim glow on the light, whereas here with our strong electrolyte, we get a really bright glow. It's carrying a lot of current through the solution. Okay. All right, again, reviewing here, a non-electrolyte does not dissociate at all. It does not break apart into charged particles. It stays in solution as neutral molecules, which means it cannot conduct electricity. A strong electrolyte, on the other hand, undergoes complete dissociations. All of these formula units, if we're talking about our ionic compounds, will dissociate. We will end up with positive cations and negative anions in the solution. Weak electrolytes, we have some dissociation. In later chapters, we'll look at how do we measure the degree of dissociation, but for now, just realize that we have these three major categories of compounds. Okay, so how do we know which of these things it is? Well, strong electrolytes, there are three basic categories of substances that you're going to be looking at: strong acids, strong bases, and soluble salts. Okay, salts it's a generic term for an ionic compound. Most ionic compounds are considered to be salts. And remember, ionic compounds, these are our metal, non-metal compounds. An exception from these would be our metal oxides. Those are not considered to be salts. Our strong acids, these are the big 7 that are listed here. You do need to memorize this. Okay, you need to know these 7. And the strong bases, it's the big 8, our group 1 metal hydroxides, and then the 3 heavier group 2 metal hydroxides. Those are all considered strong bases. And again, remember, when we're talking about strong here, we're not talking about concentration. We are talking about the ability to dissociate. And when we call something strong, a strong electrolyte, we mean that all of these molecules or formula, they will all break apart completely into ions when they dissolve in water. Okay, the weak electrolytes, those are we're going to mainly focus on weak acids and weak bases. And the way you know if something is a weak acid or a weak base is that if it's a weak acid, it's got hydrogen as the cation. However, it's not one of the big 7. Okay, same thing with bases. It's a little more involved, and we're going to look at some examples of what some weak bases look like. But as far as bases that have hydroxide as the anion, on those, again, it's not one of the big 8s. The other thing, a common one that's a base, but it's a weak base, is ammonia would be another one. And again, in class, we're going to look at some examples so that you'll kind of recognize what is a base that's not one of these strong bases. And then non-electrolytes, these are our molecular compounds that we've categorized as typically involving nonmetal to nonmetal bonding. And then most of our organic compounds are molecular. Exceptions are going to be, we've got some of our organic acids and organic bases that are going to be weak electrolytes. So let's look at this. Here we have, it wants to know if for each strong electrolyte, we'll write an equation showing the dissolving process. All right, and so let's just take a look at these and identify the strong ones first. Well, calcium chloride, that's a salt. And so it is going to be a strong one. Okay, here's nitric acid. That's one of the strong acids. All right, acetic acid, that is a weak acid, so it is not strong. Sodium perchlorate, that's a salt, and it is strong. Phosphoric acid, it's an acid, but it's not one of our strong acids, so it's weak. So that would be an Na. Barium chlorate, okay, that is a salt. It's an ionic compound. Iron iodide, again, an ionic compound. Potassium carbonate, ionic compound. Carbon dioxide is molecular, so it's a non-electrolyte. Oxygen difluoride, molecular compound, so it is a non-electrolyte. All right, so now for our strong ones, we want to show how these would break apart in solution. For every 1 calcium chloride, I would get a calcium ion and 2 chloride ions. HNO3, I'd get 1 hydrogen and 1 nitrate. Sodium perchlorate, I would get 1 sodium and 1 chlorate. Okay, barium chlorate, I get 1 barium and 2 chlorates. Iron 3 iodide, I get an iron 3 and 3 iodides. The potassium carbonate, I get 2 potassium ions and 1 carbonate ion. Okay, this is the 6 basic types of reactions that we're going to be looking at in Chapter 4. In this discussion, we're going to focus on the first 2, grouped under the category of double displacement reactions. Okay, in order for a chemical reaction to occur, we have to have something going on that is going to remove something from our solution. All right, if I combine 2 things together and all I end up with are ions floating around in solution, nothing happens, we don't have a chemical reaction. So let's look to see on these couple, what is it that's happening that's going to actually create a new substance, something we didn't have before. All right, double replacement reactions, we have basically where we have 2 compounds, aqueous compounds, that combine and form 2 products that are also compounds. And in here, as you can see, the metal cations are just switching their anions with each other. And so here's our little visual. We've got the 2 guys, and we'll say their heads represent the cations and their hats are the anions. And so the products, this is where double displacement reaction would be, that the guys would just swap their hats with each other. All right, a precipitation reaction is a double displacement reaction where one of the products is not soluble. Not soluble meaning it will not stay dissolved in the solution, and we call that compound a precipitate. All right, in this case, here we've got silver nitrate and potassium iodide, both are soluble in water, and when we mix those together, we get silver iodide and potassium nitrate. The silver iodide is not a soluble compound, which means it will precipitate out of the solution. And so let's take a look at what that looks like there. So here we have above at the molecular level, and we would have, if this were our test tube where we're making silver iodide, we would have up in the solution above, we would have potassium ions and nitrate ions. And then down here, we would have our precipitate of the silver iodide. Okay? So here we have, again, this would be out in the solution. We're going to have our potassium, and we're going to have our nitrate ions that will still be out in the solution. So how do we know if we're making something that's soluble or not? Well, we have solubility rules, and you have a table that's in the Chemical Equations Handbook that you'll be using for this unit and actually throughout the semester. And that table in there does a really nice job of helping you to decide which kinds of compounds are soluble and which are not. This slide basically gives you some real general rules that you can use, but the key thing to remember is that there are rules that help you to know based on the formula of the compound whether it will stay in solution or not. All right, now acid-base reactions. Again, this is another type of double displacement reaction. However, we are combining an acid where hydrogen is the cation with a base where hydroxide is the anion. And so we always get the same types of products in this reaction. So that's why we kind of single these out. We're not getting precipitates to remove anything from solution. However, we are forming a molecular compound, which is the water, which making that molecule is removing the hydrogen ions and the hydroxide ions out of solution. And so that is a chemical reaction. We are making something that we didn't have before. And so let's look at a couple of these, and again, how we would figure out what the products are. So here I have the hydrogen and the silver are my two cations, and let me erase that because that looks really, no, it's not letting me choose my eraser, but that's all right. Anyway, my hydrogen is going to combine, oh, I turned my pen off, great. There we go. All right. Okay. My hydrogen is going to combine with the nitrate. The silver is going to combine with the chloride. So here I would get HNO3 would be one of my products, plus silver chloride would be the other. And if I look that up on the solubility table, I would see that the silver chloride is going to be my precipitate. Okay, now the next one down, and then of course I would balance this if it needed. That one's balanced. So on these that I'm doing on this example, I'm not going to balance them, but you would want to balance these at the end or before you wrote or went on and worked with them. Okay, so now I've got calcium combining with the phosphate and sodium that's going to combine with the chloride. So I would end up with calcium. Calcium's a +2. And phosphate is a -3. So there's the formula for that, plus then the sodium chloride. Always remember you're going to write your formulas out so that you have a neutral compound that you're forming from these. Okay, and then just finishing this up, we have the lead on this one going with the chloride, the barium with the nitrate. So I have PbCl2 and barium nitrate. And again, I'm not balancing these, but you need to do that. Okay. Let's jump down here. We've got, here's our acid with the base. All right. So we know that the hydrogen and the hydroxide are going to combine to make water. And the sodium and the sulfate, that's going to give me my salt from that acid-base reaction. Okay. And then similarly here, the hydrogen and hydroxide are going to give me the water, and the potassium and chloride will form to make the salt. So see, in the acid-base ones, I'm not making, this is This is an aqueous salt and an aqueous salt. And then the fact that I'm making these non-electrolyte, these molecular waters, that's where the chemical reaction comes in there. And as we get into writing net ionic equations, you'll see a little more about why that piece of an acid-base reaction is what actually makes it a chemical reaction.